What if I told you that a broccoli could win a Nobel Prize in math? The math behind broccoli is the branch of math known as fractals. And today, I'm going to tell you all about the hidden math in nature, from fractal broccoli to logarithmic spirals in our galaxy. The list of examples is endless. Pine cones, sunflowers, viruses, galaxies, hurricanes, and so on and on and on. As you look at this list, which is continually growing as scientists and mathematicians find more and more links, you start to wonder, why are there so many instances of math in nature? This is because humans actually didn't invent math. We learned it from... Nature has had math for as long as there has been nature, a few billion years before humans were around. To prove my point, I have highlighted 5 unique and interesting examples which I want to show you all today, starting with everyone's favorite, broccoli. This is the broccoli in question, Romanesco broccoli, also known as fractal broccoli by mathematicians. You can already see it doesn't really look like a normal broccoli. It is a near-perfect example of a fractal, a unique type of shape in mathematics. You can see I've highlighted 2 regions, a bronze one and a gold one. Imagine that you take a camera and click a picture of the bronze region. Then you zoom in on the camera and click a picture of the smaller gold region. If you look at the 2 pictures side by side, you cannot tell that the 2 pictures are different sizes. They look like the same part of the plant. This is the definition of a fractal, an object that shows self-similarity within itself. This broccoli fractal goes on for quite a while, like you've got the broccoli, and then you've got a smaller part of the broccoli which looks the same, and then smaller, and then smaller. But there are some fractals, like the Mandelbrot set and Sierpinski's triangle, which are they go on forever, just getting more and more complex. The most amazing thing about the broccoli fractal, or fractal broccoli, is that it is completely made by nature, as in humans did not breed this broccoli to show this unique trait. It is completely a result of natural selection. And fractals only began to be studied extensively in the late 20th century, so this broccoli is on par with current mathematical research. My next example has to do with something called the golden ratio spiral, which is also related to the golden ratio, found in beaches all over the world in the standard spiral shell. The golden ratio, denoted by the Greek letter phi, which is basically a circle with a line through it, is approximately 1.61803398887, but it's also represented by the crazy infinite fraction in the middle of the which has far too many ones than I would have liked in a fraction. This golden ratio appears in many natural spirals in nature, and it's denoted by the black line on the picture to my left. If you look at the black line and then you look at the actual Nautilus shell, they have a strikingly close resemblance. They are both types of logarithmic spiral, spirals which just grow by a certain amount every rotation. The Nautilus, being a logarithmic spiral, helps it because it helps the Nautilus stay buoyant in water as it is an underwater creature. And it also lets the Nautilus have more space as it grows. Not bad for a sea creature, only about this big. Another small creature with complex behaviors is the periodical cicada, an insect known for mass crop destruction when it comes out of the ground. The periodical cicada spends almost 10 years maturing underground. Hundreds of millions of cicadas come out of the ground in an extremely short time frame. So, well, then they destroy all the crops, but I'm not going to talk about that. I want to talk about the time they spend under the ground. Imagine that this year the cicadas came out of the ground at the exact same time there was a spike in predators. Well, cicadas plus predators equals lunch. You don't need any math to tell you that. So the cicadas will be completely decimated. Then, let's say the cicadas come out of the ground every 15 years. And the predators, there's a spike in predators every 5 years. 15 years later, in 2038, there'll be another cicada apocalypse because 2023, there's lots of predators. 2028, there's lots of predators. 2033, there's lots of predators. 2038, there's also lots of predators. But imagine instead that the cicadas came out of the ground every 17 years. Then it would be 2108 before the cicadas were eaten by the predators in mass numbers. This is because the problem is effectively what is multiple of the amount of years a cicada takes to come back and the amount of years the predators take to come back. Prime numbers that are large are the best way to increase this number. And this is what we see in cicadas. They only come out of the ground every 13 or 17 years, which are both prime numbers. For example, Brood X in the USA only comes out of the ground every 17 years. Although honestly, I would prefer if cicadas came out of the ground and they picked the number 7,703 years. That's a prime number, and also, I don't really like insects much, so I'd prefer if they just stayed in the ground. My next example is called the Virahanka-Fibonacci numbers, also known as the Fibonacci numbers. They're the sequence at the top of the screen. It looks complicated, but it's actually pretty simple. You start with two ones. 1 plus 1 equals 2. 1 plus 2 equals 3. 2 plus 3 equals 5. 3 plus 5 equals 8. And so on and so on. It actually has almost infinite applications in nature. For example, a picture of some yellow wildflowers growing in a field in Sharjah, taken by me, is on the screen. If you count the amount of petals on each flower, you'll see that they each have 13 petals, which is the Fibonacci number. And I know this because I counted each of the petals myself. And there's another example of Fibonacci numbers in something called Fibonacci phyllotaxis. Phyllotaxis means plants want the most amount of sunlight to hit their leaves because they want to make enough food. So they try to arrange their plants in the best way possible to make sure that each of the most amount of sunlight. And Fibonacci phyllotaxis means using the Fibonacci numbers to achieve this, which can also be seen in my succulent, which I have here. It's also on the screen. Basically, if you count the amount of spirals, it will be consecutive Fibonacci numbers. Like here, it's like 5 spirals going clockwise and 8 spirals going counterclockwise. But if you have a really big example, it might go up to 34 spirals going clockwise and 55 spirals going counterclockwise. Also, if you have Fibonacci phyllotaxis, you also have something related to the golden ratio. It's called the golden angle, which is approximately 137 degrees. It's the best angle for spacing leaves around a stem. There's another relation to the golden ratio, which is shown behind me. I just started dividing some of the Fibonacci numbers. So 1 by 1 is 1, 2 by 1 is 2, 3 by 2 is 1.5, and see as it goes lower down on the screen, it stabilizes somewhere around 1.61. And if you look at the number 5, which is the golden ratio behind me, it's extraordinarily close to that. I've also divided the 4000th and 4001th Fibonacci numbers. It turns out to be exactly accurate to pi for about 10 decimal places. So as you get larger and larger Fibonacci numbers, the division of them will become closer and closer to the number 5. Well, from the elegance of the golden ratio spiral, we now go to something that's rather more chaotic. Example 5, chaos theory, the butterfly effect, and strange attractors. Chaos theory deals with finding order out of disorder. It means that you're trying to find a pattern underlying a seemingly random process, like the weather. And one of the key principles of chaos theory is called the butterfly effect. It states that if you have a butterfly flapping its wings somewhere down in Argentina, that tiny movement in air can eventually change the path of storms all the way up in Kansas. A very tiny change, like imagine you had the temperature of 20 degrees Celsius, and then you change it to 20.00000001 degrees Celsius. If you wait a few weeks, that tiny difference will grow the weather, which will eventually result in an extremely big change. And there's a concept of strange attractors. Strange attractors are modes that the weather tends to settle into. Like, I really love chess, so my strange attractor would be sitting at a chessboard and trying to beat someone. For the weather, it might be you have a high pressure system which is accompanied with long days of sunshine, and that keeps on popping up again and again and again. It's like something that the weather likes, and it likes to be in that state. If meteorologists identify these stable things, then they can predict the weather much better. So this has a real application. Although it still doesn't explain why the weather forecast is wrong half the time, since it only applies to some scenarios. So, by showing you these 5 examples, I just want to prove to you that math is found everywhere in nature. And sometimes we humans can learn a thing or two from it, even now. The Shinkansen bullet train in Japan is incredibly high speed. But the engineers hit a roadblock when they realized that there were problems with the design of the train. They looked to nature and found out that the kingfisher's incredibly aerodynamic beak was the perfect solution for their problem. A few modifications and the train was working perfectly. Even in recent years, new branches of mathematics have been discovered from nature. In 1982, a crystallographer found a seemingly which was called a quasicrystal. It had something called 5-fold symmetry, which was considered mathematically impossible until then. So, it was realized that quasicrystal was possible, and then a new branch of mathematics linked Penrose aperiodic tilings to these quasicrystals. So, we are learning new things from nature all the time, and if you ever catch yourself thinking that humans invented math and we're smarter, you should look to these examples and realize that nature has a trick or two up its sleeve. So, lesson learned. Next time you're struggling with your math homework, ask a broccoli.